this section is on continuity and evaluating limits to show that that condition is held. The definition of continuity, and I'm going to asterisk that right here, is huge. You're going to see that next year in calculus, and it's something that it's a fundamental. So here are the three conditions. So you're choosing a value C where you want to check continuity. And this part right here means that f of C is defined. That means there is a y value. And that means a y value that's defined. So not a puncture hole or something of that nature. The second condition is that the limit at that value exists, and you're going to check both one-sided limits. That means you're going to check it from the left and from the right and make sure that they come at that value. And then the last one is that the limit as we approach that value and the y coordinate are the same. And if that holds, then we're going to say that the function's continuous. Now, if we go back to a commonplace definition of continuity, which is no break in the graph or the pencil test, you'll be able to tell by looking at photos kind of what's up, but we'll have to still show that based on the definition. Okay, so let's look at our first example. Looking at a lot of these are piecewise truly. So what we're going to do in the top part, remember, we're going to try to factor out an x, and that's going to give us 2x plus 1, and that's all over x, and those cancel. So that means there's a hole at 0. And if I plug 0, so this guy's going to act like 2x plus 1. And if I put the 0 in, I have a hole at 0, 1. So if I go to my graph, and it says I have a hole at 0, 1, and then I'm going to go up 2 over 1, up 2 over 1, and that's going to let me draw. And down 2 over 1, and that's going to give me this. And then it says the function value over here, f of 0 equals 0. So that means I have a closed circle right there at the origin. Let's see if I can make that a little bit bigger. Okay, so now we are ready to run the test. So number 1, we are checking continuity at our boundary value at 0. So f of 0, I'm looking for the colored circle in my graph, that's a 0. Now step number 2, we want to check the limit as x approaches 0 of our function. So this means that we are going to have to check it from the left and from the right. So the limit as x approaches 0 from the right. Now we go back into what we were working on last week. And as we come from the right-hand side of the graph, coming from the right, we see that our y-coordinate at 0 is a 1. Likewise, if we come into 0 from the left-hand side, we can see that our limit is a 1. So our limit is a 1. So right now we haven't run into any snags. Both our conditions are holding. And now we're going to look at step number 3. So I'm going to evaluate if the limit as x approaches 0 of my function is equal to f of 0. So we look back at step 1 and step 2, and we find that our function value was 0, but our limit was 1. So that would be a no, and then we'll use our 3 dots. Therefore, not continuous. So the point to be made here is that in continuity, puncture holes matter, where in limits we can have a limit at a puncture hole, but when we're talking about continuity, we have to look at that a little bit differently. Okay, let's look at this one. So this is a fundamental graph. It's one of the ones that you have to know how to do, so we can go over here and we'll graph that already. We know, let me get a little bit more. So let's graph that top branch first. I have a point at 1, 1. We know there's a vertical asymptote at 0, so that will approach this way, and a horizontal asymptote at 0, so that approaches that way. And then down here, we have a point at -1, -1, and under those same two premises, for horizontal asymptote and vertical asymptote. And there is our graph. So now we're ready to start looking at limit conditions. So the first condition, trying to move my box, there we go. My first condition is tell me the function value at 0. Well, at this point, my function value at 0 would be undefined, because as I look at my graph, there are no points. It's a vertical asymptote, so it's undefined. Once one of the conditions isn't met, we can say therefore not continuous, and then that one would be done. Okay, moving on to the next one. So one here where we were able to go through all three. One where the first condition didn't go very well. And now let's see what happens with this one. So let's do a little simplifying first. We can factor the top by difference of 2 squares. And so I factored that out, and that tells me there's a hole at x equals 1. And we know this whole thing is going to act now like x plus 1. So my actual hole, if I put it back, is at 1, 2. So I come up to my graph now. Okay, at 1, 2, I put a hole, and then I apply my graph in that direction and in that direction. So there's my graph. And now I am ready to see what happens based on our formal definition. So step number 1, I would like to find the value of f of 1. And if I put f of 1, I get a 2, but technically there's a hole there, which is undefined. So that makes f of 1 undefined. And so therefore, this is not continuous. Okay, so those are 3 different examples that you can see where I showed all 3 that are not continuous. What will happen is if the 3 conditions are met, then you'll have a continuous function. Paralleling with limits and continuity is something called the intermediate value theorem. And what it talks about is I have to have a continuous, it has to be continuous on the closed interval. And where you see here f of a and f of b, that means that the y coordinates of the endpoints of the interval aren't equal. And k is another y value. So it's saying that there's one number that when I find the y value in that interval, it's going to possess the value k. Now there are 2 implications of intermediate value theorem, and we're going to use this not only today, but you'll use it next year in calculus. So the first thing you're going to do is find the y coordinates of the endpoints. So that means I have to find f of 0, and if I plug that into x squared plus 2x minus 1, I get -1. Then I'm going to find f of 1, which is 1 squared plus 2 times 1 minus 1. And then when I add that together, I get a 2. And what we're looking for, remember, if it has a 0, I am looking for a sign change. Okay, so I'm looking for if a one y value is positive and the other one's negative, then that means when I'm connecting them with their graph, I'm going to cross my x-axis, and that's where the 0 is. So here's the explanation that you need. Since f of 0 is negative and the f of 1 is positive. Okay, so since the y-coordinates, 1 is positive, 1 is negative, the graph crosses the x-axis between 0 and 1. So what this means for us is that therefore there is a 0 between, that there is a 0 in our interval 0 to 1. And of course the explanation is important because we're understanding that component. So now we're going to do an example that requires a little bit more legwork. So it says verify that the intermediate value theorem applies, number 1, and number 2, find the value of C guaranteed by the theorem. So the first thing we have to check, and this is a polynomial, so it has to be continuous on the closed interval, which is 0, 5. And so it is continuous because polynomials are continuous everywhere. And then we're going to find the endpoints of the intervals. So f of 0, plugging it into my function, is -1. And f of 5, plugging that into my function. So 5 squared plus 5 minus 1 is 29. Okay, so we've got that. And we also know that that value, 11, needs to be between those two numbers for it to hold. So then the implication of that is that that y value that we're looking for, or the value of C that we're looking for, needs to be between -1 and 29. So now we're going to find out what that is. So if we come up here, we're going to take x squared minus 1, or sorry, let me get rid of that. Oops, let's try to copy that right. How about x squared plus x minus 1, and now we're going to set that equal to our y coordinate, which is 11. Now I'm looking for the x that will produce 11. This is quadratic. Get a side equal to 0, and then we're going to factor. And when we factor, we get x equals -4 or x equals 3. Our next job at this point is to check. This one we're going to cross off, and the reason is it's outside the interval. And this one we're going to take. So that means, since our x is 3, that means our C value is 3, and it was f of 3 that generated the 11. And as I look at your work, even in this different setting, I will be checking for the process, not just throwing it in the graphing calculator and then looking at your table. So the work, make sure as we sit there that you show the validity and why it holds.